Hi, I'm Doug Nix. I'm one of the authors at Machinery Safety 101, and I'm also a partner at Compliance Insight Consulting. In our second Q&A video here, I'm going to talk a little bit today about the second hot question that came out of our machinery safety talks this year, and that is the application of Category 2 and test intervals when it comes to how those systems integrate their diagnostics. So for reference today, the main standard is going to be ISO 13849 Part 1, but I have also provided some references in the notes below the video. So if you hear me talking about other things or you see some little square bracketed footnote numbers, you know where to find the additional information that we're talking about today. Okay, so Category 2 is actually an architecture which we don't often see used in industrial machines. It is possible to do that. It's a single channel architecture with some diagnostics. So it's better than Category B or 1 in terms of reliability, and will actually allow you to get to performance level C, D, or E, depending on what it is you're trying to do. What we see with most clients in most machines today is Category 3 architectures or 4. Category 3 lets you get to performance level C, D, or E, and Category 4 is used exclusively for performance level E. So basically, I'll show you in a sec a little bit how that relates to risk. So the architecture we're talking about is this one. This is the logical block diagram for Category 2. And as you can see, we have a main channel that's formed from the I, L, and O blocks. I is the input device, could be a light curtain or an interlock device or even an e-stop button, something like that that's sensing a person's presence in some way or sensing the position of a guard. The L block is the logic block. This is where the decisions are made about how the state of the input device is going to be handled. And of course, the O block is the output device. That's normally a contactor or something like that that's switching power. And in between those blocks, we have the IM lines. Those are basically just interconnecting means between those devices, so wires, or theoretically it could be fiber optics or anything, but typically it's wiring. And then we have the TE and OTE blocks. So TE is test equipment. That's basically the thing that is monitoring the function of the main channel and is diagnosing any faults. And the dotted lines that you see, the M dotted lines, show you that there is some diagnostics there, but not necessarily a very high percentage. Category 2 starts out with a minimum requirement of 60% diagnostic coverage, and it goes up a little bit higher than that. And then we have the OTE, which is the output of the test equipment, and that is simply what happens if a fault's detected. The OTE actually is the alert function. It could be a light or a buzzer or something else. Okay, so that's basically the architecture that we're looking at. So when we start talking about test intervals, the first thing that we need to think about is when those tests occur. So the first place that they happen is at machine startup. Okay, so you power the machine up and the system should go through some sort of a diagnostic to make sure that it's functional and ready to operate. And then the next stage that the tests happen at is at the point where you're prior to initiation of a hazardous situation. So this is at the point where you're going to start hazardous motion or some other function in the machine. So those are the first two criteria that we need to look at. All of this happens during the designated machine lifetime, okay, the mission life, which is 20 years. I talked about that actually in our first QA video as well. And it also assumes that we're in the portion of the life where constant failure rates happen. So I just want to show you the bathtub curve so that you can see what that looks like. So when we talk about normal failures in the life of a piece of equipment, if we take a sample of all of those, all the pieces of identical equipment that have ever been built, and we sample from cradle to grave how long it takes for different types of failures to happen over the number of units that are produced, we get a curve that looks something like this, okay? And we call it the bathtub curve because it looks a little bit like the profile of a bathtub if you section one. So at the beginning of life, we have what they call infant mortality. This is the failures that happen in the factory before the products are actually shipped. They happen during quality testing and also during burn-in and so on, normal end-of-line testing. And then we get into the middle portion of the life that we call normal life. And during that portion of the lifetime, the failure rate is considered to be essentially constant. It may not be exactly constant, but it's close to that. And then we get into wear out, where now the number of failures starts to accelerate and eventually goes to theoretically to infinity. And that's when we're in wear out. So as far as machines are concerned, and as far as 13849 and industrial machinery safety is concerned, we're dealing with 20 years. That's the spec lifetime. So that normal lifetime where the failure rates are essentially constant, that's that 20-year lifetime. So that's the 20A in the middle. A stands for years. Okay, so that's the bathtub curve. So when we talk about the mission lifetime, that's what we're talking about, is that 20-year normal time. So the other 2 points that we need to think about that are unique to category 2 are that the demand rate has to be less than or equal to 1/100th of the test rate, or another way to say that is the test rate has to be 100 times the demand rate. Okay, so if we are testing, or if we have a demand rate of once per day, then in theory we need to test at least 100 times per day in order to meet this requirement. And something that was new that was added to 13849 in 2015 is that the mean time to dangerous failure, MTTFD, of the channel, so this is now the active channel, that's the failure rate of the combined of the input, logic, and output devices. The test equipment has to have at least half the MTTFD value. So if we calculate the channel MTTFD and for a number, let's say that it's 50 years, then the test equipment has to have at least 25 years MTTFD in order to conform to the requirements of category 2. Okay, so I want to show you just a quick example here, and this is completely made up, so don't ask me to show you a specific schematic for this, but the first thing that we need to do after we've done a risk assessment is then to determine what performance level that we require. Basing it on typical industrial machines, the severity of injury will be an S2, so that means we need more than basic first aid in the event that an injury occurs. The frequency we're going to call out at F2, and there's some interesting language at the bottom of the slide here that talks about the selection of F2. Basically, unless there's no better justification, you need to pick F2. If there's some other justification that you can come to, then you may be able to go down to F1. But one of the key things is that accumulated exposure time can't exceed 1/20th of the overall operating time. So, for every 20 hours of operation of the equipment, access through, let's say, through a guard door interlock this way couldn't be more than 1 hour in 20 in the normal operation of the equipment. So we pick F2. Probability of occurrence of the hazardous event is a P1, which is the lower selection of the two. And I picked that because in a minute you'll see with category 2 we can't get above performance level D. So if you follow the line across, starting at 1 to S2 to F2 to P1, we come out to a PLR of D. All right. So that's how we, using the performance level selection chart in Annex A, that's how we get to that value. So the next thing we have to do, now that we know what we're looking at, is we need to look at Figure 5 in the standard. And actually, in the next example slide, I pulled the figure from a different source, but basically it's the same. So in figure 5, what you'll see is bands, and if you look across horizontally, you'll see the performance level bands, A, B, C, D, E, okay? And each one of those bands is then sliced based on the category, and you'll see the categories along the bottom of the figure. So we have category B through 4, and associated with each category we have a diagnostic coverage, DC average. So when we look across those, we get to an area where we're at category 2, and if you look for performance level D, we could do it with either DC average of low or DC average of medium. Okay, so that basically drives what proportion of the dangerous detectable faults we're going to be able to diagnose with the diagnostics. And the red box basically shows you what I selected there, category 2, DC average of medium, okay, for performance level D. And then on the extreme left-hand edge of the diagram, you'll notice there's a listing of PFH. Okay, so that's the PFHD along the side, and it shows you basically the breakpoints in the performance level bands for each of those performance levels. And if you watched our Q&A number 1, where we were talking about safety PLCs and lockouts, I babbled on quite a bit about PFHD. Well, this shows you a little bit more about what it was I was talking about. The other thing to notice is the coloration of each band. So you'll notice we have like a dotted area, then a hashed area, and then a black area. So that speaks to the mean time to dangerous failure in the channel. So that's the active channel of the system, input, logic, and output. When we calculate the MTTFD of the channel, if we're going to achieve category 2 performance level D with a DC average of medium, you can see that the section of the strip that covers that is black, which means we need a high level of MTTFD for the components in that channel. So, all right, have I confused you yet? I hope not. I'm going to take you now to the next stage, which is where we now figure out what our design constraints are based on figure 5 and the performance level and so on that we've selected. So again, reminding you, here's the logic block diagram. This is the architecture we're working with. Our MTTFD in the channel is high, which means it's going to fall somewhere between 30 years and 100 years when we do the calculation in the channel. Our DC average is medium, which means that we have to be able to detect somewhere between 90 and 99% of the dangerous failures. So yes, you need to do an FMEA and understand what your DC average coverage is. We have CCF coverage greater than 65, so there is a checklist in Annex F of the standard for common cause failure. That's what CCF stands for, and you have to score 65 or better because we have diagnostics. We know I've set our demand rate at 4 times per hour, so we're going to open this guard 4 times per hour, which means we need to test at least 400 times per hour. And also that our test equipment, MTTFD, the MTTFD in the test channel, has to be somewhere better than a half of the MTTFD of the channel. So we're going to be somewhere between 50 years and 15 years on the low end, depending on what the channel MTTFD is calculated out to be. Okay, now in the next slide, and this is, I'm going to actually show you an example circuit. I haven't calculated all this stuff for you. This is just an example of a hardwired version of a category 2 circuit. I have to tell you that I did not take any time to assess any particular components that might be used or anything like that, so it is what it is. There are some problems, and I'm going to show you what those are. So this is a hardwired interlock that essentially meets category 2. We have a single interlocking device, SW1, that's connected to the guard. It's a direct drive device. You can see the little circle with the arrow next to the to SW1 there that tells you it's a direct drive device. So that means that when we open the guard, the motion of opening the guard is positively mechanically coupled to the interlocking device, which will drive the contacts apart, and that will result in the switch opening even if the contacts weld. Okay. S1 is the start button or the start switch for the circuit. So basically what happens is in the normal state, K2 is off, and we have the contact in the coil to KM1 closed for K2. K1 is also off, so its contact in the branch that powers the coil of KM1 is open, so KM1 is off, the motor is not on at this point. When we push S1, if KM1 is welded, then the feedback contact will be open. Okay, so that will prevent us from putting power to K2, which means that at that point now we can't actually get power to K1, right? Because if you look at the first branch in the circuit, you have to be able to get power through the contact in KM1 to the coil of K2 to get K2 to pull in before K1 will pull in. So at this point now, if KM1 is welded, then we can be confident that the system is not going to power up. So KM1 is effectively monitored. KM1 is not welded, then its auxiliary contact in that start loop will be closed. So that means we get power through the normally closed contact on K1 to the coil of K2. If that happens, K2 pulls in, which then applies power to the coil of K1. K1 seals itself in with its K1 contact, the normally open one. It also opens the coil circuit to K2. And when that happens, K2 drops out, and because K1 and K2 are now closed in the case of K1 and in the normally closed state for K2, coil of KM1 is energized, the motor energizes and the machine starts. Okay, so that's cool. We've looked after all that stuff. There are a bunch of faults that can't be detected. And if we go back and actually look at the block diagram for category 2, you'll notice that we have monitoring in the input device. Well, this circuit has no monitoring to the input device, so it doesn't actually meet the requirements of category 2. So this is a circuit diagram that I actually pulled from a reputable manufacturer's website. Now, admittedly, they didn't say that it met performance level D or anything like that, but it was called out as a category 2 circuit. So that's a problem right away. There's no monitoring. We do have monitoring in the output device. So the O is effectively monitored, so that's good to go. And of course, the test equipment is only the auxiliary contact for KM1, so we're not testing anything beyond that. We do have some testing from the point of view of the interaction between K1 and K2. If K2 welds, it's not possible to turn KM1 on because its normally closed contact will stay open if K2 is welded. If K1 welds, you can't energize K2 because the normally closed K1 contact will be open, and so therefore you never get power to the contact or to the coil of K2. So there is some testing of K1, K2, and KM1, but the one thing that's notably absent from this is SW1 has no testing. And you could modify the design of this circuit so you had some testing for that. You could take a second contact from SW1 and put it in the feedback circuit, and as long as it was closed when the guard was closed, then that would at least tell you that you had 2 contacts in that device that were agreeing. One more point I need to make about the category 2 circuits, and this may not be apparent to you if you haven't read the definitions recently, but because a category 2 circuit like the one that we're showing here, and let's go back to the block diagram. When you look at this block diagram, the active channel, so the I, L, and O blocks, that's a single channel. So one of the fundamental things about categories B1 and 2 is that a single component failure can lead to the loss of the safety function. So if we look at the schematic diagram here, you can have a failure in SW1 cause a loss of the safety function. You can have a failure in K1, a failure in K2. If K2's coil goes open, then it's possible to have a loss of the safety function in there. Also, and the most important one, obviously, is if KM1 welds, and yeah, we have testing for KM1, that's lovely, but if KM1 welds, it doesn't matter what the state of the rest of the circuit is, that motor's still turning. And with this particular circuit, the only way to shut the motor down would be to pull the fuses or the disconnecting means for the main supply that powers whatever's connected to KM1. So the testing that is present in this circuit is, in my mind, really not adequate at all for a true Category 2 application. And so if you're considering stealing the circuit diagram and using it in your machine design, I highly recommend that you don't do that, because you are likely going to be sadly disappointed in terms of how it actually performs. Okay, so be aware, each of the architectures has some unique benefits and downfalls. And one of the key things about the single channel architectures is that a single failure can cause the loss of the safety function. And if you're talking about an S2 level of injury, so something that's more serious than basic first aid, then having the safety system fail in a way that results in your losing control of the machine is probably not acceptable. And I think that's one of the main reasons why we don't see these used in industrial machines very often. It does happen, but not very often. And usually in equipment where the severity of injury is lower than S2. Okay. You'd also have to look at mechanical failures in SW1, and there's not really any good way within Category 2 to detect that. So after you do your FMEA and you come up with all of the various failure modes of all the components that you're using in your system, you can then determine what the diagnostic coverage is overall. The other thing that you will not be able to do with a discrete component circuit like this is there is no repetitive testing in this. It only happens at the moment of the demand on the safety circuit. So the moment you open the guard, that's when it happens, or when you start the machine, that's when the test happens. But you don't have the cyclic testing that's required as part of the definition for what Category 2 has built into it. So basically, you would need to add some additional test capability to this to get the cyclic testing requirements at that 400 tests per hour. So in all honesty, the best way to achieve Category 2, if you really are intent on doing that, is to use an off-the-shelf safety relay that's designed that can be actually implemented in Category 2. Basically, most of the relays that are out there can be implemented in that way. So you can do that using, for instance, dual channel input. One is basically the test loop for the switch. So channel 1 is in the main contact, channel 2 is in the auxiliary contact. That gives you the testing for SW1, and then just use a single output contactor with monitoring through an auxiliary, and that basically would give you what you need. The off-the-shelf devices typically have a lot of additional testing built into them that are needed for Category 3 and 4. And so basically you shouldn't have any difficulty meeting the test requirements for Category 2 if you use one of those other relays and configure it appropriately. Okay, so that's the end of the story for Category 2 and test intervals. Use a COTS device, common off the shelf is COTS. Use a COTS safety relay to design and build your circuit with, and you should be good to go. Hope you enjoyed this little video, and if you have any other questions, you can leave them in the comments below the video or below the blog post, depending on whether you're seeing this on YouTube or on Machinery Safety 101. And you can always email me if you have any other comments or concerns that you'd like me to address privately. Okay? Thanks again. Look forward to seeing you in our next Q&A video.